Before your phone wakes, before your car moves, before your world even begins, one silent technology decides everything. And now, humanity is running out of it.
The world runs on tiny pieces of silicon. Yet today, these tiny chips have become the core of the greatest technological struggle on Earth. From factories in Asia to design labs in California, a fragile chain of atoms and electrons holds up our economies and our future.
Factories designed to build billions of chips now stand silent, victims of a supply chain stretched to its limits.
Demand exploded. Computers, vehicles, servers, AI. Yet the world had too few fabs to meet the rising hunger. Every quarter the graphs climbed, and the red lights flared like warning beacons across the globe.
Then the pandemic struck. And the supply chain cracked like never before.
The United States responded with urgency, launching massive plans for new chip factories.
Billions in investments began to pour in. Yet money alone could not solve the crisis.
China, too, accelerated. Building colossal megafabs, determined to dominate semiconductor independence.
Meanwhile, Taiwan, the heart of global chip making, felt the pressure of rising demand and global tension.
For decades, the world relied on a fragile yet unstoppable path, Moore's Law. As transistors shrank, we doubled the power again and again. Integrated circuits, microprocessors, dual cores, and now advanced AI chips.
Today, those tiny circuits power everything. And their shortage threatens industries across the globe.
One defect, just one microscopic flaw, and an entire batch of chips can fail. Here, a void no wider than a strand of DNA is enough to turn cutting-edge silicon into worthless glass. It lurks in a lattice of billions of transistors.
As shortages spread, entire industries froze. Automakers, appliance makers, even defense contractors.
Markets panicked as companies struggled to secure even the simplest microcontrollers.
Production lines that once built thousands per hour now stood powerless, waiting for chips that never arrived.
Governments took action. None more dramatic than the U.S. CHIPS Act, a bold attempt to rebuild American semiconductor power.
New megafabs began rising from deserts, farmlands, and industrial zones. Massive monuments to a new era.
Answered with scale, unprecedented construction, and a national mandate to dominate chip manufacturing.
But the rarest machines on Earth, if lithography systems, became the most critical bottleneck of all.
Nations tightened export controls, stamping barriers across cutting-edge machinery, blocking code, and freezing shipments. A geopolitical maze now surrounds the world's most advanced chip tools.
As time passed, prices soared.
and the global competition for semiconductor power grew fiercer than ever.
Designing a modern chip requires billions of transistors and a level of precision humans can barely comprehend. Layer by layer, connections thinner than a strand of DNA must align in perfect harmony.
But without enough fabs, even perfect designs were useless. There was nowhere to manufacture them.
Automakers watched helplessly as millions of vehicles sat unfinished, waiting for a single missing chip.
Even hospitals felt the shock. Life-saving devices delayed because a chip wasn't available.
Global shipping collapsed under pressure, and the world began searching for answers.
Corporations pledged billions to build new factories, yet construction would take years.
The world realized that chips weren't just technology. They were geopolitical leverage.
Cyber battles erupted as nations raced to protect their chip secrets and steal others.
Even the raw materials became weapons. Gallium, germanium, cobalt, once simple elements in a periodic table, now controlled, restricted, and strategically priced.
And by 2030, demand is expected to double, forcing nations into the most intense factory race in history.
Across the world, megafabs grew. Tall, metallic, breathtaking, the new cathedrals of technology. Here, steel and silicon meet under the hum of cranes and the sparkle of welding arcs.
Alliances formed, partnerships strengthened. In boardrooms and on factory floors, signatures turned into shared commitments. Nations realized they could not face the chip crisis alone. Together, they built a resilient, connected future.
Artificial intelligence demanded more chips than ever, pushing manufacturing capacity to its limits.
At the heart of the revolution stood EUV, humanity's most complex machine.
With each generation, 5 nanometers, 3 nanometers, and beyond, the world entered a new frontier.
But with progress came risk. The more vital chips became, the more vulnerable the world grew.
Impact from 5 to semiconductor industry may surpass $3 trillion, reshaping economies worldwide.
Nations began planning not for the next year, but for the next century. From every corner of the world, tiny sparks of innovation connected, weaving a lattice of light over our planet. Foundries, once isolated, now beat in synchrony.
And on the horizon emerges the next generation, chips that are smaller, smarter, and even self-healing. Here, legions of luminous microbots patrol valleys of metal and glass, sensing breaks no human eye could see. They weave light into lattices.
In a world powered by silicon, the race for chips is more than competition. It is the future itself, being built before our very eyes.
The chip crisis will end, but the race will not. For every nation, every company, and every dream of the future depends on what we build next.